Imagine you're walking through a busy city, crossing a street, maybe waiting on a train platform, or even just driving your car. How often do you pause to think about how incredibly safe these everyday activities actually are?
Probably not very often, right?
Exactly. We largely take for granted the massive, complex systems that silently work to protect us, especially in critical industries like railways. We talk about risk all the time, but truly understanding, measuring, and managing it, particularly when human lives are at stake, well, that's a deep, fascinating rabbit hole that's far more precise than most people realize.
And that's precisely the rabbit hole we're diving into today. Our focus is the sophisticated world of railway safety, and we're going to zero in on an indispensable analytical tool known as FN curves.
FN curves, okay.
Yeah, and these aren't just abstract mathematical concepts tucked away in engineering textbooks. They are fundamental to how safety professionals, engineers, and even policymakers grapple with incredibly vital questions like, how do we balance individual safety with the collective well-being of thousands? What does safe enough truly mean when designing a system that impacts so many lives?
Right. Our mission in this deep dive is to unpack how these statistical tools provide the bedrock for making informed decisions, ensuring the robust management of potential hazards, and ultimately keeping countless people safe every single day. For you, whether you're an engineering student, an early career professional, or just someone inherently curious about the world around you, you'll gain a shortcut to being genuinely well-informed about the hidden mathematical backbone of safety that underpins our modern infrastructure. Let's start by laying some essential groundwork.
Sounds good. To truly appreciate the power and purpose of an FN curve, we first need to get incredibly clear on what we mean by risk within the context of safety engineering. It's a term often thrown around loosely, but in our field, it has a very precise, actionable definition.
Right. It's not just a vague feeling of danger or a gut instinct. In safety engineering, risk is meticulously defined as the combination of two critical elements.
Two things, yeah.
First, you have the probable rate at which a specific hazard causes harm. How often is this potential danger likely to turn into something real? And second, it's about the degree of severity of that harm. If something does go wrong, how bad could it really be?
Exactly. So it's about understanding both the likelihood of an event occurring and the magnitude of its potential consequences. It's the product of these two factors that truly defines the risk, not just one or the other.
Okay, makes sense. Likelihood times severity.
What's crucial to grasp here is that we're talking about a chain of events, not just a single isolated incident. It begins with a hazard. Just anything with the potential to cause harm, think of it as a loaded gun just sitting there.
It's just potential energy, sort of.
Right. Then, an initiating event acts as the trigger, setting things in motion. This leads to a sequence of consequence events, a series of unfortunate steps that cascade one after another, ultimately culminating in an accident and its associated damage, whether that's injury, fatalities, or property destruction.
Like dominoes falling?
Precisely. Imagine a runaway train. A hazard might be a worn-out brake pad. The initiating event could be the driver attempting to slow down on a steep incline. The consequence events are the brakes failing, the train picking up speed and derailing. The accident is the derailment itself, and the damage is what follows. We're trying to predict and, more importantly, prevent those dominoes from falling.
And this detailed, almost forensic understanding of risk isn't just an academic exercise. It's absolutely fundamental to practical safety management. It's what underpins our ability to determine safety integrity levels, or SILs, for complex systems. These are predefined levels that specify the required reliability for safety functions.
SILs, yeah, very important.
For instance, a system controlling train signals that could prevent a head-on collision would require a much higher SIL than, say, a passenger information display.
That makes sense. Higher risk needs higher integrity.
This precise definition of risk also allows us to calculate what's called residual risk. This is that irreducible level of risk that still remains even after we've implemented all our safety measures, from advanced technology to rigorous operational procedures.
Because you can never get to zero risk, realistically.
Right. We can never eliminate all risk, but knowing what's left and ensuring it's within acceptable societal limits is absolutely crucial. It helps us direct our resources to where they'll have the greatest impact.
Now, a critical and, honestly, often overlooked aspect of truly defining and quantifying risk is what we call exposure.
Exposure, okay.
This isn't just about how likely an accident is in general, but specifically how much an individual or a group is actually subjected to that hazard. It's the time spent in harm's way, or the amount of interaction with the risk source. This factor can dramatically change how we perceive, compare, and manage risk.
Here's where it gets really interesting and frankly quite counterintuitive for many people. Think about an activity like bungee jumping. If, tragically, someone were to die during a jump, it's an awful catastrophic event.
Yeah.
But if you try to calculate the risk of dying per hour of uninterrupted bungee jumping, that number would be astronomically high, perhaps even misleadingly so. Why?
Because the actual time you're exposed to the direct critical risk during a single jump is just a few fleeting seconds of free fall itself.
Just those moments.
Yeah. The actual relevant risk for a bungee jumper is per jump, or perhaps per year for someone who jumps frequently, which factors in their limited intermittent exposure. That short exposure duration fundamentally changes how we think about the risk value. Calculating per hour makes it look absurdly dangerous compared to, say, driving.
This same principle applies directly and profoundly to railways. Consider a vehicle driver approaching a railway level crossing.
Right.
Their risk isn't a constant continuous value over the entire day. It's tied to their specific exposure time, the brief moments they're actually interacting with or near the crossing.
Just those seconds or minutes they're actually on or near the track.
Exactly. Similarly, for a track worker or a train driver, their risk isn't uniform. It's linked to the specific time they spend on the tracks, in the cab, or near automatically closing train doors. The risk profile shifts dramatically based on those precise windows of exposure.
You can be in the vicinity of a railway for hours, but your direct exposure to the operational hazards is often very limited, relatively speaking.
And what's particularly tricky, and often a point of confusion in international safety discussions, is that different safety standards, and there are many out there, like IEC 61508 for functional safety, or EN 50126, specifically for railway applications.
Even ISO 25119 for agricultural machinery, funnily enough, has relevant principles.
Right. They all use exposure time in varying ways. This means that comparing safety levels across different industries, different systems, or even different countries can be incredibly difficult and misleading if you're not absolutely clear on the parameters and definitions of exposure being used.
It really highlights why nailing down this exposure conundrum is so essential for accurate, comparable risk assessment. Without that clarity, you're often comparing apples to oranges or even apples to abstract concepts.
Oh, yeah, absolutely. Okay, so we've got individual exposure. What about the bigger picture?
Moving from the individual lens, let's broaden our scope and talk about collective risk. This is precisely what it sounds like: the potential harm to a defined group of people.
Like passengers on a train.
Exactly. Passengers on a train, the various railway personnel like train drivers, signalers, or track workers, or even third parties such as people living near railway lines or using level crossings. Each of these represents a distinct risk group with its own unique exposure patterns and potential consequences.
Now, for the sake of simplification and standardization in analysis, especially when looking at the broader picture of collective risk, we often focus on fatalities. That sounds a bit stark, though.
It does, but it's crucial to understand that severe and even slight injuries are by no means ignored. They're actually converted into what we call equivalent fatalities.
Equivalent fatalities, how does that work?
It's a mechanism to account for the overall burden of harm. For instance, a common practice in railway safety is to consider 10 severe injuries as statistically equivalent to one fatality.
Okay.
And furthermore, anywhere from 10 to 20 slight injuries might be considered equivalent to one severe injury. So it's a way to weigh different levels of harm.
So if a single train incident resulted in, say, 20 severe injuries and 100 slight injuries, how would that calculate out?
Well, using that method, the 20 severe injuries would count as 2 equivalent fatalities. The 100 slight injuries might convert to, say, 5 to 10 severe injuries, which then converts to maybe 0.5 to 1 equivalent fatality. So you'd add those up.
I see. So this standardization allows us to measure overall harm in a consistent and comparable way, ensuring that every type of harm contributes to the risk picture.
Exactly. It avoids just focusing on the absolute worst outcome and gives weight to serious harm, too.
So how is this collective risk actually calculated in a meaningful way?
The probability of an accident occurring that results in a certain number of fatalities or equivalent fatalities for a given risk group depends on 2 primary factors.
Okay.
First, you have the overall likelihood of a specific accident scenario actually happening. For instance, a derailment at a certain speed on a certain type of track. How often might that occur?
Right.
And second, you need to consider the conditional probability that a certain number of people will be killed or injured if that specific scenario does occur.
So the chance of the event and the likely outcome if it happens.
Precisely. It's a multi-layered, probabilistic calculation that seeks to capture the full spectrum of potential outcomes.
This raises an important question. How do we statistically model accident data, especially when these accidents, thankfully, are generally rare and occur independently of each other?
That's a great question. The answer is often through something called a compound Poisson process, or CPP.
Compound Poisson process sounds complex.
It does, but the idea is quite intuitive. Imagine accidents not as single isolated points, but as jumps occurring over time. A standard Poisson process models the rate at which events happen randomly and independently over a fixed period.
Like calls coming into a call center.
Exactly. Now, at the compound part, each time an accident occurs, it has an associated jump height, which in our context is the number of fatalities or equivalent fatalities.
So not just when it happens, but how bad it is.
Right. So a CPP helps us track both the frequency of accidents and the accumulated severity over a given period, creating a much richer picture than just a simple count. It's like counting how many times a bell rings, but also how loud each ring is.
Okay, that makes sense. And this CPP model connects to the FN curves.
And this is precisely where the FN curve comes into play as an incredibly powerful visualization and analysis tool for collective risk. An FN curve plots the probability, represented by F, of an accident occurring as a function of the minimal number of persons, represented by N, killed during that accident.
Okay, so F is probability, N is number of fatalities.
Minimal number, yes. So Fn essentially tells you the cumulative probability of having accidents that result in N or more fatalities within a fixed time interval, typically a year.
So F10 would be the chance of an accident killing 10 or more people in a year.
Exactly. For example, if F10 is 0.001, it means there's a 0.1% chance in any given year of having an accident that kills 10 or more people. This curve provides a quick, intuitive snapshot of the overall risk profile of a system or operation. You can see at a glance how likely different levels of catastrophe are.
What's particularly insightful and sometimes a bit counterintuitive for those new to this is that N in the FN curve isn't about counting unique individuals who are harmed once. Instead, it's about the cumulative exposure.
What do you mean?
Well, for example, if you're a regular commuter and you take 10 train trips in a year, for the purpose of modeling collective risk, your exposure to the railway system's risk is factored in for the duration of each specific journey, not as a continuous singular presence.
Ah, okay. So in the collective risk model, your exposure on those 10 trips contributes to the overall N, similar to how 10 different passengers taking one trip each would.
Exactly. This abstract view helps us model the collective exposure more accurately, reflecting the cumulative risk exposure across many journeys and individuals over time. It's about the potential for loss of life hours or life journeys, if you will, not just discrete bodies.
Indeed, the importance of duration, or exposure time, cannot be overstated when interpreting these curves. For trained personnel, their exposure time per year is generally more fixed due to stringent regulations governing their working hours and specific roles. They have a more predictable interaction with the system.
Right, their work schedules define their exposure more clearly.
The key takeaway, then, is that even if collective risk is expressed per calendar year for simplicity, accurate interpretation requires careful consideration of these varying exposure times for different risk groups. A low collective risk number might hide high individual risks if exposure times for a small group are very high, or vice versa.
That makes sense. So you always have to ask exposure for whom and for how long. Now, let's zoom in from the collective, the broad sweep of passengers and personnel, to the individual. Individual risk. That sounds more personal.
It is. Individual risk zeroes in on a single, arbitrary, often fictive, average person. It's about their personal probability of being killed or injured over a defined period, say, an hour of exposure or a full calendar year. This is the risk you might feel yourself if you were to engage in a particular activity or be part of a particular risk group.
The what's the chance it happens to me question.
Pretty much. To calculate this individual risk accurately, we need to make some very specific and realistic assumptions about how exposed that individual is to the risk.
Okay, assumptions like?
For instance, when analyzing the risk for a typical passenger, how many train journeys might they make in a year? And crucially, how long are those journeys on average? Some standard analyses might assume a typical passenger makes, say, 500 journeys a year, with each journey lasting, for example, half an hour. These assumptions are vital and must be clearly stated as they directly impact the resulting risk number.
Right, change the assumptions, change the number, which directly leads us to calculating a personal exposure time.
Exactly. If someone takes 500 train journeys at half an hour each, that's 250 hours of actual personal exposure to railway risk per year.
And that calculation lets us link back to the collective risk.
It does. This calculation is what allows us to convert a broad collective risk into a meaningful individual one. Essentially, an individual's share of the overall collective risk is directly proportional to their individual exposure time compared to the total cumulative exposure time of the entire risk group.
So my slice of the pie depends on how much time I spend at the table, basically.
A good way to put it, yes. It's a way to personalize a broad risk assessment and make it relatable, answering the question, what's my chance of being harmed if I engage in this activity?
What's truly fascinating and often surprising is how dramatically risk values can change depending on the chosen unit of measurement. Is it given per calendar hour, the hour of actual exposure, or per person kilometer traveled?
This truly highlights why context and clear units are everything when discussing safety. Otherwise, numbers can be deeply misleading. It's easy to misinterpret if you don't see the denominator.
It's absolutely crucial, isn't it? Let's dive into some striking comparisons to make this concrete. Consider something as adventurous as alpine climbing.
Okay. High-risk activity, presumably.
It might have a very high death rate when you look at it per hour of actual exposure, perhaps somewhere between 30,000 and 40,000 deaths per billion hours of direct exposure to climbing hazards. That's a staggering number per hour.
Wow. Yeah, that sounds huge.
But because most people only engage in this activity for a relatively short period each year, maybe 50 hours annually for a dedicated enthusiast, their typical annual risk might actually be lower than, say, car travel.
That's right. Car travel, for example, has a significantly lower death rate per hour of exposure, roughly around 700 deaths per billion hours.
Much lower than climbing per hour.
Much lower. However, the average person spends far more time in a car annually, perhaps around 300 hours or more. So while alpine climbing has a higher per hour risk, a typical person's annual risk from car travel could be statistically higher simply because of the vastly greater exposure time.
That really illustrates why the units matter so profoundly in public perception and policy. It's easy to focus on the scary per hour number for climbing and miss the bigger annual picture for driving.
Yeah, absolutely.
And when we look specifically at railway travel, how does it stack up using these exposure-based metrics?
Well, it stands out as significantly safer per hour of exposure compared to car travel. We're talking about a typical death rate of roughly 80 deaths per billion hours of exposure for railway travel.
So 80 for rail versus 700 for car per hour. Big difference.
A dramatic reduction, yes. It's also vastly safer than many occupational risks in heavy industry, which can have hourly fatality rates in the thousands or tens of thousands. This paints a very clear picture of just how robust railway safety systems are.
And what about looking at it per distance traveled? That seems relevant for transport.
Even more impressively, when you consider risk per unit of transport capacity, like per billion person kilometers traveled, railways and civil aviation emerge as incredibly safe modes of transport.
Okay.
In the European Union, for instance, both typically show a mortality risk of around 0.35 deaths per billion person kilometers.
0.35. Very low.
Extremely low. Compare that to road traffic, which stands at a significantly higher 9.5 deaths per billion person kilometers. This metric highlights the sheer volume of safe travel facilitated by these modes, a testament to decades of rigorous safety engineering and operational discipline.
So the really important takeaway here is this. Risk data presented without clear reference to exposure times can be profoundly misleading, even questionable.
Definitely.
For instance, stating a general risk of accidents at home without specifying who's home, for how long they're at home and exposed to hazards, or what specific activities are included.
Makes that number almost useless for any meaningful comparison or actionable insight. You can assume typical working hours for occupational risks, maybe. But for something as broad as accidents at home, the range of exposure is so vast it becomes an irrelevant statistic without context. It's just noise.
Precisely. For absolute clarity and accurate comparison, risk is best presented per a general unit of exposition time, such as per hour, or for collective risks in transport, per unit of transport capacity, like per person kilometer.
Neglecting exposition time can lead to a misunderstanding of risk by an order of magnitude or more. It completely changes the picture of perceived versus actual safety, and it's a critical point for anyone involved in risk assessment or public policy.
Okay, that's crystal clear now. Exposure time is king. Now that we've firmly established the groundwork for understanding individual and collective risk and highlighted the absolutely critical role of exposure time in interpreting those numbers, let's take an even deeper dive into the FN curves themselves.
Let's do it.
We'll explore their mathematical core and see how they are used not just to represent risk, but to infer profound insights about how society views safety.
All right, let's get into the mathematical heart of FN curves. These curves usually conform to a very specific and telling mathematical form, Kn equals C n a.
K equals C over N to the power of alpha. Okay, let's break that down.
Right. Kn here represents the number of accidents that result in N or more fatalities.
Okay, the cumulative number of accidents above a certain severity N.
Exactly. C is simply a constant that scales the curve, determines its overall height. But alpha, that's the Greek letter, alpha is the exponent, and it's arguably the most important part of this formula. It typically falls between 1 and 2, but crucially, it's always greater than 1.
Always greater than 1. Why is that so significant?
So this alpha value is absolutely central because it mathematically embodies what we call risk aversion.
Risk aversion. What does that truly mean in practical terms, and why is it so important for safety policy?
It means that society, generally speaking, is significantly less tolerant of a single catastrophic accident causing a large number of fatalities than it is of multiple smaller accidents that might cumulatively add up to the same total number of deaths over time.
Right. Think about it. A single train crash killing 50 people often generates far more public outcry and political pressure for change than, say, 50 separate individual car accidents each killing one person, even though the total loss of life is the same.
Precisely. The societal preference is not merely anecdotal, it's quantified by this alpha value. A common value for alpha used in many safety regulations and calculations, particularly in the railway sector, is 1.5.
1.5.
If alpha were 1, it would imply that society is neutral to whether deaths occur in one large event or many small ones. Total number of deaths is all that matters. But because alpha is greater than 1, often 1.5, sometimes higher, it means there's a steeper slope on the FN curve as N number of fatalities increases.
So the probability drops off faster for really high N values?
Exactly. This steepness visually and mathematically represents our greater aversion to high-consequence events. This numerical representation embodies a deep-seated societal preference, often driven by factors like media attention, public fear, and the perception of control. Large, infrequent events often trigger a stronger emotional and political response.
So this elegant formula doesn't just describe historical data, it allows us to derive the overall number of fatalities expected from the curve.
Correct.
And critically, it lets us compute individual risk. We can take the parameters derived from that collective FN curve, particularly C and alpha, and combine them with an individual's specific exposure time to estimate their personal probability of harm.
It really brings together the concepts of collective risk, societal preferences, and individual exposure we've been discussing into a cohesive framework. It connects the big picture to the personal level.
But here's a vital point for anyone relying on these models. Simply plotting an FN curve or looking at historical accident data isn't enough to make robust comparisons or draw definitive conclusions about safety performance over time or between different railway systems.
Absolutely not. Accident data is inherently noisy. It's not always perfectly smooth or predictable, and it can be influenced by many external factors like weather, economic conditions, or new technologies. You can't just visually inspect two curves and declare one safer. It might just be random fluctuation.
That's precisely where rigorous statistical testing becomes absolutely essential. Remember how we talked about real-world accident data being modeled as a compound Poisson process, or CPP?
Yeah, the jumps happening over time with different heights.
Right. While often assumed to be homogeneous, meaning the rate of accidents and their severity distribution are constant over time in practice, that's rarely the full picture.
Right, things change. There are often seasonal variations due to factors like winter weather impacting track conditions, or summer heat affecting equipment. Or perhaps new safety measures are introduced, which we'd hope would shift the underlying process. So how do we confirm if these changes are real or just random fluctuations?
So you need a way to separate the signal from the noise.
This leads us to a key analytical technique, the decomposition of a compound Poisson process. To truly understand safety performance, we can break down the CPP into two main components that are often statistically independent.
Okay, decompose it into what?
First, you have the rate at which accidents occur. That's essentially the counting process or the frequency component, how many accidents are happening in a given period. And second, you have the severity of each accident. That's the jump height distribution or the consequence component. When an accident does happen, how bad is it?
Frequency and severity. Makes sense.
This decomposition is absolutely key for performing rigorous statistical analysis because it allows us to ask specific questions. Has the frequency of accidents changed? Or has the severity of accidents changed? Or both? This fine-grained analysis is far more powerful than just looking at the total number of fatalities.
So when we want to compare safety performance over different periods, perhaps looking at last year versus the average of the previous 5 years, we essentially set up a statistical null hypothesis.
The starting assumption.
Right. We assume, for the sake of argument, that safety performance has not changed. Then our job is to use statistical tests to see if the observed data provides enough evidence to actually reject that null hypothesis.
If we can reject it with a high degree of statistical confidence, then we have strong evidence that something has changed, and we can start investigating why. This is a powerful framework for evidence-based decision-making in safety.
Okay, so how do we actually do that testing? What are the methods?
One clever and robust way to approach this statistical testing is through what's called the random walk approach.
Random walk. Sounds like something from physics.
The intuition here is quite elegant. Imagine charting the cumulative difference in accident severities between two different periods over time.
So plotting how much worse or better this period is compared to the last one, adding it up as you go.
Exactly. If safety performance hasn't changed at all between these two periods, then this cumulative difference should ideally randomly walk around zero, not straying too far. It would fluctuate up and down, but generally hover around the starting point.
But if something has changed?
If, however, the curve starts to deviate significantly and consistently either upwards or downwards, that suggests a real underlying change has occurred in safety performance. This approach is conceptually similar to a Kolmogorov-Smirnov test, which looks at the maximum difference between two cumulative distribution functions to see if they are from the same underlying distribution.
What's truly fascinating here, and a reason why this method is so robust, is the power of limit theorems in this context. For a large enough number of observations, which we typically have in long-term railway accident data, the distribution of these cumulative differences becomes what we call distribution-free.
Distribution-free, meaning?
It means its statistical shape doesn't depend on the specific underlying distribution of accidents themselves, only on its standard deviation. This is a very powerful result for practical application because it means we don't have to make tricky or potentially inaccurate assumptions about the exact statistical nature of the accident distribution to perform our test. We can simply calculate the standard deviation directly from the observed data.
So it works regardless of whether accidents follow, say, a normal or exponential distribution.
To a large extent, yes, for large samples. In practice, what we do is estimate this standard deviation from the actual accident data and then establish a statistical threshold. If the observed maximum cumulative difference between the two periods we're comparing exceeds this calculated threshold, then we can confidently say, with a predefined level of statistical certainty, that safety performance has indeed changed.
So it gives us a robust tool even if we're unsure about the exact underlying stats.
Exactly. This approach is particularly valuable when specific assumptions about the underlying distribution of accidents are hard to justify or verify, giving us a powerful and robust tool even in uncertain real-world conditions. It provides a data-driven basis for making crucial safety decisions.
Okay, that's one approach, the random walk. You mentioned another one.
Another, often even more powerful and precise way to test for changes in safety performance is the decomposition approach.
Back to splitting frequency and severity.
Right. This method is based on a very sound statistical principle. Accident occurrence and accident severity are often independent events. That means the decision to apply the brakes, for instance, doesn't inherently determine how many people will be injured if the brakes fail.
Makes sense. They're separate parts of the chain.
So we can analyze the jump times, which is when accidents occur, and the jump heights, which is their severity, separately, allowing for a more nuanced and powerful analysis.
Okay, so what tests do you use for each part?
This decomposition allows us to construct two independent statistical tests, each optimized for its specific component. First, we have a test for jump times. Are accidents happening more or less frequently?
Right, the rate.
For instance, if we can reasonably assume accidents follow a homogeneous Poisson process, meaning they occur at a constant average rate over time, we can use an F-test to compare the intensity or rate of accident occurrences between two periods. This is a very efficient and powerful test if that Poisson assumption holds true. It's like testing if the average number of times a train is delayed significantly changes from one year to the next.
Okay, so that covers frequency. What about the severity, the jump heights?
And then crucially, there's the test for jump heights. Are accidents becoming more or less severe when they do occur? For accident severity, we can make different assumptions about the underlying distribution, such as a normal distribution for certain types of injury data, or more commonly, an exponential distribution.
Exponential. Why is that common?
Well, an F-test, for example, could be used to compare the equality of standard deviations between two sets of accident severities if we assume a normal distribution. Alternatively, if we assume an exponential distribution, we could compare the means. What's compelling is that the exponential distribution is often motivated by the real-world observation that the probability of very severe accidents, those with a high number of fatalities, decreases rapidly as the number of fatalities increases. It's rare to have an accident that kills 100 people compared to one that kills 10. The exponential captures that rapid drop-off.
Ah, okay. So it reflects that extreme events are much rarer. What if you can't assume a specific distribution like normal or exponential?
Good point. Alternatively, if we can't make strong specific distribution assumptions about the accident data, non-parametric tests, like the Wilcoxon test, can also be used. These tests are more robust because they don't rely on assumptions about the data's underlying distribution, although they might be slightly less powerful than parametric tests if those assumptions do hold.
So there's a trade-off between power and robustness.
Exactly. What's important to remember is that these parametric tests are generally considered optimal because they extract the maximum amount of information from the data, provided their underlying distribution assumptions are correct. They leverage the full statistical power when the model fits the reality.
Okay, so we have these different testing methods: random walk and decomposition using parametric or non-parametric tests. How do they perform in practice?
When we apply these different statistical testing methods to simulated scenarios designed to mimic real-world railway accident data, we see some interesting and important differences in their performance.
Like what?
In cases where there truly is a subtle but significant change in safety performance, for example, a slight reduction in average accident severity due to a new safety measure, non-parametric tests, which are more general and make fewer assumptions, sometimes fail to detect that change. They might not be sensitive enough.
So they might miss a real improvement.
Potentially, yes, if the change is small. Similarly, the random walk test, while robust, might catch a change in some scenarios but not in others, especially if the change is very subtle or occurs over a short period.
And the parametric tests.
However, the more powerful parametric tests, those specifically designed for certain distributions that often characterize accident data, such as the Poisson for frequency or exponential for severity, are often able to clearly and consistently identify even nuanced changes in safety performance, for example, changes in accident frequency or average severity.
So if you can justify the assumptions, they give you more power to detect real changes.
Precisely. This highlights a crucial point for you, the listener. Simply looking at aggregate numbers like annual national reference values for safety performance isn't enough. These headline figures don't capture the full granular picture of accident times, frequencies, and severities. They can smooth over important trends.
So just looking at the total number of fatalities year on year isn't the best way.
It's often insufficient. Instead, using these rigorous statistical tests, which are based on these detailed accident characteristics, the precise timing and severity of each event provides a far more reliable, scientifically sound way to assess changes in railway safety. It moves us beyond a simple count of fatalities from one year to the next to a much deeper, more dynamic understanding of the underlying safety dynamics of a complex system. It tells us not just what happened, but potentially how and why it changed.
That makes a lot of sense. Getting into the details gives you much more insight. So we've explored how FN curves represent collective risk and how rigorous statistical tests confirm changes in safety. But what's even more fascinating and perhaps less intuitive is that an FN curve doesn't just describe collective risk. It can actually reveal the underlying statistical distribution of accident severities itself.
Really? How does that work? It's like looking at the shadow and understanding the object casting it.
Exactly. Here's where it gets really interesting for those who love connecting theory to practice. When you mathematically derive the probability density of accident severities from a typical FN curve, the one we discussed with the KN, little CNA form,
Yeah, the alpha one.
it turns out to be a specific type of distribution, the Pareto distribution.
The Pareto distribution, isn't that the 80-20 rule thing?
It's famous for that, yes. The Pareto distribution describes phenomena where a small number of events account for a large proportion of the total. Think of income distribution, where a relatively small percentage of the population earns a large percentage of the wealth.
Okay.
In safety, this means that a few highly severe accidents contribute disproportionately to the total harm. For example, a single major derailment might cause more fatalities than dozens of minor incidents combined over several years.
So the big ones dominate the overall picture.
Exactly. This is a crucial insight for risk management because it tells us where to focus our mitigation efforts. Preventing those high consequence, albeit rare, events, even though they're rare, their potential impact is huge.
Knowing this, we can take real-world accident data and, using statistical methods, estimate the key parameters of this Pareto distribution, especially that crucial shape parameter alpha we discussed earlier.
And what does estimating alpha tell us?
This allows us to do several powerful things. We can predict the likelihood of future accidents of certain severities, compare severity distributions between different railway systems, or analyze trends across different time periods. We can also use statistical goodness of fit tests to see how well the Pareto distribution actually fits the observed accident data in practice. Does the theory align with reality?
That's powerful. Can you give an example?
A compelling real-world example of this is the analysis of Swiss railway accident data over a decade. When they applied these methods, the estimated shape parameter for accident severity derived from their actual accident history fell perfectly within the commonly accepted range used for FN curves, typically around 1.5 to 2.
So the real data matched the theoretical model based on the FN curve structure.
Precisely. This wasn't just a theoretical exercise. It empirically demonstrated the practical applicability and predictive power of these statistical models in a real-world, high-stakes railway safety environment. It shows these models aren't just academic constructs, but powerful tools for understanding and managing risk.
That's really compelling. It validates the whole approach.
Now, while the Pareto distribution offers a great general fit for accident severity, a closer, more granular look at extremely detailed accident data, especially when you consider how slight, serious, and fatal injuries are very precisely defined and weighted for analysis, might reveal a more step-like distribution rather than a perfectly smooth curve.
Because the categories are discrete.
Potentially, yes. This suggests that for super fine-grained analysis, where every minute detail and every weighting factor matters, even more complex statistical models might be needed. But for broad, robust risk assessment and policy, the Pareto distribution provides an excellent, foundational, and incredibly useful starting point.
Makes sense. A good model, even if not perfect, down to the last decimal place. So, what have we truly unpacked today? Let's recap.
Yeah, let's pull it together. We began by recognizing that simply defining risk isn't enough. We need to meticulously consider individual and collective exposure.
Right. Understanding how the time unit, the definition of the exposed population, and the context profoundly change how we perceive and measure risk is absolutely fundamental. This is why a simple, decontextualized number like accidents at home is so often misleading. It lacks the necessary granularity of exposure.
We then explored the profound power of FN curves as a fundamental tool for representing collective risk. We saw how they reveal critical insights into societal risk aversion, particularly with that alpha parameter,
which mathematically demonstrates how much less tolerant we are of single, catastrophic events that result in many fatalities compared to a series of smaller incidents that sum to the same total. This tells us about public perception and policy priorities.
And finally, we dove deep into the absolute necessity of rigorous statistical testing. We moved beyond simple aggregated comparisons like annual national reference values to truly understand subtle but significant changes in safety performance.
We explored powerful techniques like random walk tests and decomposition approaches, which allow us to analyze changes in accident frequency and severity independently. And perhaps most surprisingly, we learned how FN curves can even reveal the underlying statistical distributions of accident severities, specifically the Pareto distribution, which highlights the disproportionate impact of a few severe incidents.
This deep dive isn't just about abstract statistics or complex mathematical formulas. It's about equipping you with the mental tools to look beyond the headlines, to ask the right questions, and to truly grasp the nuances of safety in complex, mission-critical systems like our railways.
It's a shortcut to being genuinely well-informed, whether you're an engineering student grappling with design challenges, an early career professional stepping into a safety-critical role, or simply an engaged citizen who wants to understand the world around them more deeply.
As future engineers, current professionals, or simply engaged citizens who rely on these systems, you now have a clearer picture of the mathematical backbone of safety and the sophisticated tools used to manage it.
So consider this. What does this deeper understanding mean for how you approach safety designs or risk assessments in your own work? How might recognizing these nuances, the role of exposure, the meaning of risk aversion, the power of statistical testing, and the implications of the Pareto distribution shift your perspective on what safe enough truly means in a complex, interconnected system like a railway?